Welcome to the course Mastering Algorithms Analysis and Application. This session is about performance analysis, especially the space complexity. So how the performance analysis of an algorithm is done? There are many criteria to judge the performance or the quality of an algorithm, but two important criteria were identified. One is the space complexity, other is the time complexity. So what is space complexity? The amount of memory an algorithm needs to run to complete is called as the space complexity. So in the memory space, how much memory has been utilized by an algorithm is called your space complexity. And what is time complexity? The amount of computer time an algorithm needs to complete is called as the time complexity. So here is the formula for calculating the space complexity. So space complexity SP is given by C plus S to the base P. So what is the C? C defines the fixed part and which includes the space which are utilized for instructions and the space for variables which are independent of your input and output characteristics and the space for constants. So these spaces includes fixed part component and this S to the base P includes the variable part component which includes the space for variables which are dependent on input and output characteristics. Here it is independent, but here it is dependent. So that is the difference between fixed part and variable part. And the space for any reference variables that we have utilized and recursion stack space. So all these comes under variable part component. So in case of a recursive algorithm, and non-recursive algorithm, what to be considered in fixed and variable part? That is a big confusion. So in non-recursive algorithm, we will solve some example to get a better idea. Consider this as an algorithm which is used for swapping two variables A and B. Here I have used a variable A. So space for that variable is 1. I have used another variable B. Space for the variable is 1. I have used the third variable temp. So the space for another variable is 1. So totally it is 3. Since it is a constant, the order is 1. Consider the next example. Here is an algorithm which has an array of size n, and we are introducing a variable n, and there is a loop. The solution is, we have an array of size n. So to store n elements, I need space n. Then n is another variable. For storing n, I have 1. I is another variable. For storing I have 1. So the sum of all these, that is n plus 2, will be the space complexity. So it is represented as O of n. Coming to the third example. Here this algorithm is used to calculate the sum of all the elements in an array. So I have used an array which is of size n. So to store n numbers, I need n space. Then n is a variable. So to store n, I need 1. S is another variable. To store s, I need 1. I is another variable. To store I need 1. So sum of all these is n plus 3, and it can be represented as order of n. Next example. There are two matrices A and B, and this algorithm computes the addition of two matrices. So the solution is, to store the resultant matrix, I need n into n. For matrix A, I need n into n. For matrix B, I need n into n. Then I am using a variable n. For that one, I'm using a variable I, I'm for that 1. I'm using variable j for that 1. So if I add all these, it is 3n square plus 3. So it can be represented as order of n square. The next example is multiplication of two matrices. So I have two matrices of size n square. The resultant matrix is also of size n square. I have three variables I, j and k, each of size 1, 1 and 1. There is a variable and another variable n, for that also 1. So if I sum up all these, it will be 3n square plus 4. So the order will be n square. The space complexity will be order of n square. Suppose if it is a recursive algorithm. So the examples that we have discussed are non-recursive algorithm. So if at all the algorithm is recursive, then I need to consider the recursion stack. So what will be there in the recursion stack? The local variables, the actual parameters and the return address. These three has to be considered for a recursive algorithm. So for each recursive call, these three has to be considered. And then the space for these three components will be allocated in the recursion stack. And we need to also identify the depth of recursion. That is how many times the recursive call is made. So once we have identified these three parts, then we can calculate the space of recursive stack as depth of recursion into space for all the three components. So this is the formula. Depth of recursion and the space for three components. These should be multiplied to get the space for the recursive stack. So here is an example. This is an algorithm wherein this function is recursively called here. So again and again this function is going to be called. So the solution is, so the depth of recursion, how many times will this function be called? That is depth, n plus 1. And for each recursive call, we need to identify the three parameters, the local variable, the actual parameter and the return address. Yes, the local variable here, there is nothing. And the actual parameters, I have two. This is one actual parameter, this is another actual parameters. And the return address, yes, I have one return address. So the space complexity is given by n plus 1 into 3. Summation of these will be 3 and the depth will be n plus 1. So n plus 1 into 3, so it is order of n. Next example, finding the factorial. Here the depth of recursion will be n plus 1. There is no local variable here, so 0. The actual parameter is only 1. This is my actual parameter, so it is 1. Yes, there is a return address 1. So SP is given by depth of recursion into local variable plus actual parameter plus return address. So that is n plus 1 into summation of this 2, which is 2n plus 2, that is nothing but order of n.